And we can talk about general derivatives. So for example, the derivative for x squared you might have caught on is going to be 2x. So if I know that, then f prime of 3. So if f prime of x is 2x, then f prime of 3, again, we're just going to plug the 3 in. So this is going to be 6. And f prime of negative 5, negative 10. If I'm looking for the value of x for which the derivative is 0, well, that's just where the derivative is 0. So that's at x is equal to 0. Here I'm looking for where the derivative is 5, so that's x is equal to 5/2. And for e, we have to do a little bit of work. We need the average rate of change of f of x equals x squared over 19. Well, I know a rock is going to be 81 minus 1 all over 9 minus 1 is 8, so that's 80 over 8, right? So this is my first part. Second part, where is 2x equal to 10? Well, that's going to be at x is equal to 5. For question 2, I need to use the definition of derivative to determine a derivative formula. Well, I like this one better. I'm going to use the limit as x approaches a of f of x minus f of a over x minus a. And this is going to be the limit as x approaches some number a of x cubed minus a cubed over x minus a. But I can factor the top, the limit as x approaches a of x minus a times x squared. Let's see, this is going to give me plus ax plus a squared all over x minus a. So suddenly, that troublesome factor cancels out. And as x gets very close to a, or I'm going to say as a gets very close to x, they become interchangeable. So this is going to become, I'm going to write it in terms of x squared. This is going to be x times x now, because x is close to a. This is going to become x squared. So the derivative of x to the third is 3x squared. I'm going to do the same thing with x to the fourth. Let's see what that looks like. The limit as x approaches a of, I'm going to have x to the fourth minus a to the fourth over x minus a. And I'm going to factor the top, the limit as x approaches a. I'm going to have x squared plus a squared. And then I'm going to have x squared minus a squared, which I can factor into x plus a, x minus a, all over x minus a. So suddenly, I'd no longer have indeterminate form anymore. X is getting very close to a, so I will use them interchangeably. My x squared, I'm going to have x squared plus a squared times x plus a, which is just going to become x squared plus x squared times x plus x. So I have 2x squared times 2x, which is going to give me 4x to the third. So if our function is x squared, the derivative is 2x to the first. X to the third becomes 3x to the second. X to the fourth becomes 4x to the third. So I'm thinking if we have something raised to a power, the derivative is going to be n times x to the n minus 1. And we can prove that. So if that's the case, we can use it. And I'm going to rewrite f of x. This 1 over x I'm going to write as x to the negative 1. So therefore, the derivative is going to be negative 1 times x. I'm going to subtract 1 from the exponent to the negative 2, or negative 1 over x squared. 1 over x squared, I'm going to rewrite as x to the negative 2. So that f prime of x is going to be negative 2x to the negative third, or negative 2 over x to the third. If I have square root of x, I can write that as x to the 1/2, so that the derivative is going to be 1/2 x. I'm going to subtract 1 from 1/2. That gives me negative 1/2. And if I want, I can write the derivative as 1 over 2 root x. This cube root of x I can write as x to the 1/3, so that the derivative is 1/3 x, subtract 1 from the exponent, to the negative 2/3. And 1 over square root of x, I can rewrite that as x to the negative 1/2. So then when I take the derivative, I'm going to bring down that exponent. I'm going to subtract 1 from the exponent. So that's going to give us negative 1 over 2 times the square root of x cubed. Or if you like, you could simplify that square root of x squared. Square root of x cubed. And that's it.